Improving Society in less than 30 minutes. The short podcast of Körber-Stiftung. We all know that good things take time. However, most of the time we don't know if it's going to be worthwhile. Surprisingly, the tiniest things often have the power to change the world. Anthony Hyman, a cell biologist working in Dresden, has shown that focusing on one particular subject can lead to new groundbreaking discoveries. He's the winner of the Körber European Science Prize in 2022. In this episode, he will surely change the way you look at biological cells. Improving Society with Anthony Hyman. Moin.
Good morning.
So moin is the Hamburg version of hello every day times,
morning,
really.
Exactly, yeah. Also used in Dresden, having said that, moin.
No.
I hear that quite often here.
Well, we're going to talk a lot about the East and about Dresden as well. But first of all, congratulations to winning the Körber Prize 2022. Your research is focused on cells, something that is happening within the cells. And those tiny, tiny little things that you've discovered in some things called the threadworm, which might not be familiar to many people out there. And it's only 1 millimeter long. So could you try to break it down for us so that a grandmother would understand?
Well, the way I like to describe it is that, we consist of trillions of cells. And each one of those cells is an incredibly complex, you might call it city. Or you could even call it a world, because it has about 5 billion proteins in each cell, which is roughly the population of the world. So you could think about the similar problem. If you just arrived from Mars and you wanted to study the world and you just studied individuals, you and me, you'd understand something, but you wouldn't really understand how society is organized. And so the question then is, how is society organized? We have factories that make cars, or we have power stations that make energy. And similarly, the cell has places that it does certain things, like the mitochondria you might be familiar with, that make energy.
Yeah.
Some of you might remember that from high school. And what we discovered was there's a form of organization which is more like a flash mob, where like 1 million proteins come together quickly, do something, and then go away again. It's like you wanted to build a car, and instead of building a factory, you had a flash mob, the radio was on, 1 million people came together, they built it, and then they disappeared. And the discovery that was interesting from the science side is that these factories that were formed had all the behavior of liquid droplets.
Right.
And from the science point of view, that opened up a whole new set of ways of thinking about how they're organizing it and how you could maybe interfere with that if you wanted to cure some diseases.
Speaking of liquids, when it's cold, water turns into ice, a process that follows laws of the physics. And you work with quite a similar thing. Can you explain to us what it is?
We use the concept of phase separation, which you're very familiar with. If you make a vinaigrette, you add oil and vinegar and you mix them and you go to the door to let the guests in. You come back, it's separated into oil and vinegar. And that's a process known as phase separation, or Phasentrennen in German. And the most common time you see that is in clouds. Clouds condense.
Right.
The water droplets that form these clouds, or ice and water, as you say. So this is a process that you see throughout the physical world.
Like a fat separation container, when you cook, you sometimes get it, that you can separate the fat from the juice of the sauce.
Yeah, that's another phase separation. The fat is on top of your stew and you scoop it off with a slotted spoon. That's a similar kind of thing. And of course, you can make it mix by putting a detergent in, by washing up liquid, or mixes again, because then you solubilize the fat molecules in water. And we discovered this type of Phasentrennen, phase separation, inside cells.
And these condensates, how are they important for the cells in general?
As I mentioned before, cells don't do things with individual proteins. It'd be a little bit like not using sociology to study the world, just individuals. Some people would like that, of course. Some people believe in the individual, but we know that society works through interactions. And so if we're going to understand how the cell does something, we have to understand how it's constructed. Like if you wanted to understand how a village made bread, you'd have to go to the bakery and find out how it all worked. Let's say bread started coming out bad. you couldn't fix that unless you understood how the bakery worked. It's an oven. And so it's the same for us, right? We need to understand how these things work if we're going to understand how to fix them.
And even more, it's like you might talk to the baker about it, but then there's a lot more to it. Like, what ingredients are you using? Where do these ingredients come from? And I bet it's probably about as complex as it is with cells. You've just hinted at the fact that it might have an impact on curing degenerative diseases. So we're talking about Alzheimer's or ALS. Can you tell us a bit more about that? Because that would be fantastic, wouldn't it?
Yes, we haven't worked on Alzheimer's, but we worked on ALS. And what we discovered, with others in the field, was that these liquid-like compartments, so often they form a liquid compartment inside the cell by phase separation. Now, what liquid means is that the molecules are moving around all the time, right? If you know that if you take a bucket of water and you put some dye in there of some sort, it'll all diffuse until it's all blue. What we discovered is sometimes these liquid-like compartments harden, we called it. The molecules stopped moving around so fast, it got slower and slower and slower.
Right.
And then out of those hardened compartments, these aggregates started to grow. The doctors see when they look in patients who died from ALS. So we called it a liquid to solid phase transition. In other words, a liquid compartment becomes more solid. And one of the ways to think about what do you mean by these terms, liquids and solids, et cetera, et cetera. One example I often give is like a school. The first thing that happens is the kids and the parents are all distributed around the city, maybe in the cafes, whatever there. And then suddenly there'll be the bell will ring and there'll be a phase separation. The kids will go to the playground and the parents will do something else, right? The kids are running around in the playground. They're constrained because they know they shouldn't leave the playground, right? You don't have to build a wall. You can tell the kids, look, here's a white line. You're not allowed to leave that. And they don't leave it because they want to play with themselves, each other, rather than move away. Good. So that's like a liquid. Then what happens is the bell goes and they all have to sit down and study. And then they are in the same place. And that's like a solid, right? So that's the difference between a liquid and a solid is that in a solid case, they're all sitting down in their places. And the liquid, they're all moving around. What you can imagine then is they all sit around and then maybe they sat down on glue. And they couldn't leave. And then they're stuck. And that's a really bad state, right? And then, bad things happen, And so that's in a way what happens when the solid starts. They all get stuck in this place and then that can have bad consequences to the cell.
I bet that kids can totally relate to that image. I mean, being stuck to the chair at school is something they experience every day and they don't like to
be. They hate that image. Now, how would you solve that? You look for a chemical that stops them sticking. For instance, you come in and do something, and that's what we try and do as basic scientists, and look for chemicals that might stop that process.
You put a chemical in, and is that connected to the energy system of the cell, the ATP that you write about?
Well, there's two things. One is what we try and do to fix it by using chemicals. The other thing is what the cell tries to do, where they may use ATP. And there are special machines. It's an incredibly complex process, mind-numbingly complex. And the average person doesn't need to know the details, just need to know the cell has an incredibly complex set of machinery, which uses ATP often, but not always, to try and unstick the things that are stuck together in the wrong way.
I see. Let's get back to what you focus on, the chemicals. Chemicals could lead to medication and therefore be the cure to certain diseases. Drug research is actually one aim of the research on condensates. And obviously, I'd like to know how long you think it will take until we finally have something that you think will help with the treatment.
You start off designing complete new medicine. It takes decades to do it. It needs to take decades to be safe. The public has to trust the process. People often ask, why not make it faster? But then once you get mistakes, drugs start doing damage, you can set back the whole process. But think about the following. You have a known drug. And it didn't work quite as well as you'd hoped. Why not? Well, the more you understand about the cell, the more you might understand why it doesn't work. So let's say your disease protein is contained in one of these liquid condensates, and you add a drug. You swallow it, it goes into the bloodstream, it goes into the tissue, it has to get into the cell, but it also has to get to the right condensate. It's like in a village, right? You send a letter. It first has to get to the right village. Then it has to get to the right factory. Then it has to get to the right person. Mm-hmm. So it's useless if the letter gets to the village, it doesn't get to the right factory. It'll never get there. Or if it gets to the factory and goes to Mrs. Smith instead of Mr. Jones. And that's exactly what the discovery's already helped, is thinking about, can I make my chemicals that are known work a little bit better? Because curing disease is not, something that happens today, tomorrow. It's disease cures happen in steps, little steps each time. I like to use the example, which we don't work on, of HIV and AIDS. When we first started making chemicals, you had a little bit longer life, and now they had different ones. And now that you can hold people, people aren't cured, but they survive for basically a long, long time. And so anything we know about the cell helps us take these steps forwards towards the cure.
And would you take it even further? Like we've just talked about Alzheimer's, ALS, and a drug, obviously. Would you take it to a higher level?
In what sense?
Like you're going to the very basic thing of our human body, the cell. Yeah. So can it have an impact to more than these parts that we talked about?
The concepts of phase separation in general, people often use them to think about tissues and how we form animals. But I think it could be general in the following sense that I think what the discoveries of condensates show is the power of physics in helping understand biology. And this interaction is very, very powerful. So from that sense, you're correct, because it shows that we should use physical concepts as much as we can to help us understand biological problems. And the working together of physicists and biologists is essential for moving forward. In academia, these disciplines tend to be isolated. You have the Department of Physics, Department of Biology, Department of Chemistry. We all know that, right? And so the crucial thing is to have structures that allow this overlap.
You've just said that things take time, as all good things take time. Yeah. And you've discovered the condensates in 2009. Now we have 2022. It seems like a long time. But what has happened since then? The
basic discovery, actually in 2008, we published in 2009, but discovery was 2008.
Right.
All we discovered was a compartment in a small nematode were liquid-like. And that's true for all discoveries in biology. You find some little interesting nugget of information, and you don't know how general it will be. And we didn't know either. But then the more we did, the more we realized, wow, this is general. This compartment's also liquid-like. This is also liquid-like. And that took us another 2 or 3 years. And then the big breakthrough in 2015, when we and others realized that it could be related to disease, 2015. And there was a big explosion of work where everyone started to really get on with it. So this is how basically discovery works. There's 2008 is a discovery, but there was decades leading up to that, right? I started my lab when I was 30, so that's 1992. So 16 years later of all those, we've made this discovery, but everything led up to it. And then it's the 10, 20 years afterwards that exploit the discovery to show how important it is.
The listeners couldn't see that you were like smiling when you talked about the big breakthrough. Any of those moments, do you still remember them in a specific way?
Yeah, you remember those moments for the rest of your life. It's like sometimes I talk to sports people and they say the same thing. A particular moment sticks in your mind. These are etched in my memory, where we were, who said, how we said it, who said what, this pumping of the heart, this sweating of the palms. I've only really had it twice in my career. It's an incredible and indelible feeling that makes it all worthwhile.
And when was it that you've had this feeling? Was it back in 2009 that you already anticipated, well, this might be...
No, we knew when we saw it, this is really, really interesting.
So in 2008? Then?
2008, yeah. We knew how interesting it would be. We didn't know how interesting, but we understood it was really interesting.
Did you know that it was something that was able to change the way we think about the human body? Or at what time did you think that?
Well, it was a very exciting discovery, and we realized that if it were general, it would. I think we understood that. That's why, in a way, we made the discovery, because it's not enough to observe things. I think people in the past, some people had observed liquid-like states, and then people have proposed it going all the way back to the early 20th century. What was crucial about us, I think, is we had the right people together who understood the implications of it. And that's often what it's about, right? It's not just making the observation, it's having the right pre-knowledge to understand the implications of what you see.
Absolutely.
As my supervisor used to tell me when I did a PhD, Tony used to say, it's not enough to write a paper. You've got to write papers that appeal outside your small field. That's always the goal, right? Because if you can get a discovery out to the wider world, then you suck people in who can use their expertise to try and exploit it.
I think this is a very inspiring statement, because to all these scientists I've talked, it's so many times, especially when it comes to the PhD, about publishing, getting things out and not making a difference.
Yeah.
And you hinted at the importance of intersection. You were talking about, obviously, about biology and physics, but also chemistry and many more. And then getting it out to the public is another thing. Applications is another thing. Also, your institute is in Dresden. You're British. So what do we need to do to get things out, and how important is this intersectional work?
Let me step back and say, what do we do as scientists? We publish papers. That's our output. And that's why every time people want to change the publication system, I say be very careful, because our output is papers. And I just recently went back and found a paper from 1952 that some student published. I don't think it was very well particularly referenced, but it was a very important paper that I could find that made a huge difference, right? So most of the stuff we do in our career is just publishing papers. We have to publish papers that are good enough that someone else in the future, when we're all dead, could come back and reproduce them and understand why we thought it was interesting. So that's the primary thing we do. We fill the literature with observations. But the question you have is, how does your work have impact? And that impact requires you in some way to present what you've done in a way that others can understand it intersectionally. So as a biologist, how do I explain what I've done to a physicist, or the other way around? Because it's like a Tower of Babel.
Absolutely.
They use different language than we do, often describe the same thing. So first we have to learn each other's language. And that is the reason for the success in Dresden. I think these discoveries came out of Dresden because it was built to have interaction in physicists and biologists in 1998. It's been practicing. So this discovery is the flagship discovery in the sense it's been awarded prizes, but there's an enormous amount of physics and biology that's happened. So you need to set up structures that allow that to happen. And that was a wonderful thing about the wall coming down. The East, you could set up new ways of doing things that allowed you to explore new structures. And that's what we did in Dresden. It's called the Dresden model of the way that we organize our science in the Max Plancks, and it's been successful.
Let's get back to the bakery. Most people will know that you need flour to make most breads. The way you bake is unique to every baker. You mentioned machines like an oven that will have an impact as well.
Yeah.
Equally, you said that scientists with different backgrounds speak different languages. And then presenting your findings to the public will require a whole new set of skills.
Yeah.
So what are the challenges and advantages in working with an interdisciplinary team?
Well, I mean, one way to think about it, if you want to come to your bakery, is let's say a chemist comes into a bakery.
Yeah.
And wants to help, be baked better, or wants to get some ideas from the bakery about how to do new chemistry. At the beginning, they have to understand, what is this terminology they're using? What does kneading mean? What does this mean? What does that mean? And what is this vocabulary? And then they have to look at these ingredients, and they have to then study the ingredients. And what are they? And there's flour. What is flour? It's flour. But for the chemist, flour means what type of flour? What kind of chemicals are in there? So that would be the beginning before you could even have a conversation. So you need to have systems in which there's enough time for everyone to learn their own language. And then if I could tell you what will come out of it, I would be doing it. Because, that's the whole thing about science, is that the way this good science works is the following. You put people together and you give them the right conditions. You stir the pot to get some energy into the system, and then people talk to each other, and you hope that some creative idea comes out of it that you couldn't predict before.
Coming to a more personal view on your work, you've just talked about sweaty hands and raising heart rate and all of that.
Yeah.
How has your discovery changed your personal life?
I was very lucky to go to the laboratory of molecular biology for my PhD, where they won 18 Nobel Prizes. So right from the beginning, I was told, you have to find something which is going to change the way people think. That's your goal. You may never do it, but that's be your goal. And so that means for the first 20 plus years of my career, I was searching around for something, which was my goal. I did lots of science. And then suddenly you find something, you think, yes, that is it. And then your whole personal life becomes focused in on this understanding. And that gives one a great deal of focus in life and happiness because you know what you have to do. You know what you want to discover, what you want to work on. And then all your life is focused in on this mission. I like to describe that to be a scientist, you have to be curious. So there's no point being a scientist if you're not curious about the way the world works. But you also have to have what I like to call commitment to the mission, 20, 30 years where you do nothing else. But to do that, you need to know where you're going. If you're trying to climb Everest, you don't know how you're going to get there, but you know you want to do it. You have some mission. And then I knew what my mission was, to understand this problem and communicate to physicists what we learned in biology and understand what physicists did, communicate it back again. And so that gave me this wonderful sense of freedom, intellectual freedom I was trying to do. And I also say a sense of contentment because, as I said, as biologists, in the end, as scientists, what we're trying to do is come up with an idea that sort of changes the way people think about things. And I knew I'd done that. To what extent will be come out in the future? But, you know, I changed the conversation. And that's just a feeling of contentment. I'm 60 now and I can go into retirement, think, yeah, I achieved what I set out to achieve.
I was going to say, is there something addictive? So, you know, thinking about retirement, is that even possible?
Retirement requires you to feel content with what you've done. You know, I am addicted to scientific discovery, but the older I get, the more I realize that, you know, a lot of it we should leave to young people because they have more energy and ideas, and we shouldn't take the money away from young people. So I think your role changes. You know, at the beginning, you're in the trenches, you're working, you're thinking, you're talking about the details of the experiment. It's like at the beginning, you're in a factory making sure why this bolt is attached and not properly attached. And then you got management and you start to think about strategy and help the young people understand how you design cars, as an example. And that's true in science. So you need to take a step back and say, okay, what I need to do now is help younger people learn about how to be a scientist, how to make discoveries without telling what discoveries to make. As long as you can achieve that, it's easy to sort of step back. And I think that's the great thing about my personal life, that I felt I achieved that. I have done. So that gives me a nice feeling that I can fade off into the background, content.
Well, and you've obviously ticked some boxes that many scientists would love to achieve. One I would like to highlight is in 1999, you were one of the founders of the Max Planck Institut für molekulare Zellbiologie und Genetik in Dresden. So if I may put questions about your professional part aside, why Dresden?
Well, we have a word in English called peripatetic, which is about not being able to stay where you are. You know, I grew up with a family where my mother came from a sort of Scottish aristocratic background, my father from a immigrant Jewish background. And so when you come from a background like that, you don't fully fit in. Then I started moving around the world. You know, I went to San Francisco, had a great time there, went to Heidelberg, was having a great time there. And then I was only 36. The wall had come down. They were trying to build a new institute in Dresden. And then my boss at the time, Kai Siemens, came to me and said, do you want to come to Dresden? And I thought, why not? You know, sounded cool, good adventure. I didn't think I'd settle here, but I thought it'd be a great adventure. Because here's the thing, Diana, is that if we stay in the West in places, fundamentally, most of your life, you're trying to preserve what our forefathers set up, right? When I lived in Heidelberg, the cafes are the same as they were when I arrived, and they probably were the same as they were. But Dresden is so fantastic because things are changing all the time. New this, new that, up and down. And that's a wonderful feeling of excitement. You know you're part of building something new. And so all of us who came at the time together can say, yeah, we achieved something. You know, Dresden is a major biomedical campus now in the world. And that was because we, as a collective, decided to come to Dresden.
What a nice speech for the East. Yeah. Would there be anything else that you would like people to know, something that would be your mission or that you could deduce from your career?
Maybe just coming back to what you just said about Dresden, I do often feel that my colleagues in West Germany could spend more time in the East to celebrate the achievements since the war. You know, there's often a lot of grumpiness. But one shouldn't forget the Germans with the Solidaritätszuschlag. You know, what is that, 4% now or something of taxes? I don't know what it is. Every German since 1989 has been prepared to spend 3.5%, 4%, I don't know what it is, their income tax on rebuilding the East. That's an incredible achievement. And, you know, the problem I find as a foreigner, I mean, I actually am German citizen now, is how hard it is for Germans to enjoy and celebrate what they've achieved. Because it's a remarkable achievement. I think if every West German was forced to go on a bus trip around East, they would see just what an incredible achievement it's been. So that'd be my first thing. If you're listening and you haven't done a tour of Dresden or Leipzig or Halle, it's absolutely incredible. So that'd be my first thing. And I guess the other lesson I would say is try never to be content with what you've done if you want to do something in life, right? So in other words, maybe content is the wrong words. You can be satisfied that what you've done in any moment was good, but you shouldn't be content it was enough. I think that's what my father called divine discontent, this feeling of always trying to do the next thing. Enjoy the adventure that is life, because certainly we're very, very privileged to grow up in the West. We can travel anywhere. If we have German passports, we can go almost anywhere in the world. So using that privilege to see the way different people do things is incredibly good for your life, your internal feeling, your creativity.
Talking about celebration, we are obviously also here to celebrate you winning the Körber Prize in 2022. Beforehand, we just talked about the relevance of it and that Svante Pääbo has just received the Nobel Prize. So how did the Körber Prize change something for you?
We are satisfied with what we do, and that's what you have to have, internal satisfaction, right? I mean, a good life, and everyone knows that from the beginning, is being internally satisfied and not knowing outside people to tell you how. You should think you're good looking because you yourself like the way you look, not because someone else tells you. We're all told about those things all the time. But on the other hand, we also, all of us need a little bit of, Anerkennung. That's basis of human personality. If you get recognized like that, it's a nice feeling because others have put a stamp on it. And it's a way of saying to people who aren't in your field, look, this thing that this guy did actually is interesting. So it brings other people in to help think, why was it interesting? I want to find out about it. The internal satisfaction of your colleagues recognizing what you've done and the satisfaction that it brings, the noise brings other people in to help learn about what you're doing.
And as a journalist and a psychologist, I obviously also hold the feature of being curious. What are you going to do with the money?
Yeah, that's a good point, actually. I was actually just had breakfast before then with a friend of mine because every time I've ever, had a little bit of money, some prize, whatever, I've always bought a bicycle, right? I have 10 bicycles. And now I'm thinking, I've got enough bicycles. So what am I going to do? I think there's two things. Most of the money is for research. And that money for research I'm going to put into ALS work. I think that was a good thing for me about the whole Preisverleihung was how interested the journalists were in its effect on ALS and how interested the Körber-Stiftung was. So therefore, I thought I should put the money mainly into how we're going to work on ALS. And then the private money I have, I think I will probably just get another bicycle because, I don't have much fantasy. I mean, I have, one doesn't need that much in life. But bicycles certainly make a big difference.
Any specific type?
Well, I think I'd probably a new mountain bike because every time I go to the Alps to cycle with my friend Adriana Guzzi, who lives in Switzerland, I find out that my bike has not got low enough gears. I'm struggling all the time. So a bike that's easier to pedal up the hill would be good. Up the Alps, up the mountains.
Anthony Hyman tells us to celebrate maybe even the little things in life, as we Germans sometimes tend to forget about this. Also, he wants us to be content that what we've done was enough. He is the winner of the Körber Prize 2022. I'm very inspired by your work and by the impact that it might have on ALS and other degenerative diseases. Please check out more information about this groundbreaking work in the show notes. Thank you very much for your inspiration and the insights to your work, Anthony Hyman.
Thank you so much. That was a great pleasure.